In this video, we're going to do another application of first order differential equations. In particular, we're looking at compound interest as it applies to annuities and mortgages. Now, first of all, annuities and mortgages are essentially the same thing. It just depends on which side of the transaction you're on. So, for instance, if you're buying a house and you take out a mortgage, you're borrowing money from the bank. The bank is charging you interest and you're paying them back, right? So the amount of money owed is changing for two reasons: interest being charged, payments being made. On the other hand, if you're, setting up a retirement account, you're giving money to the bank. So the bank is borrowing money from you. They're paying you interest because you're letting them use your money. And then when you set it up as an annuity for payments for like in retirement, so the bank is paying you back. Um, so the amount that the bank owes you is changing again for two reasons. You're charging them interest, or they're paying you interest, and you're taking the money out of it. So the amount they have is less because of that, but it's more because of the interest. Okay, so it's the same. Mortgages and annuities are really the same thing. It's just a matter of, which side of that transaction are you on. Okay, so here's how it's going to work. I'm going to do this problem in general. I'm not going to do a specific example here. I'm just going to leave it all in terms of the variables. So let's let P be the amount of money borrowed. Usually it stands for principal. So that's the initial amount that's owed. Let's think of it in terms of doing a mortgage. So you're going to borrow P dollars. So at time zero, that's the amount owed. Let R be the annual interest rate. So, I'm noting the labels here, the units. So we're measuring the amount owed in dollars. The annual interest rate is per year. Um, that's the label for the interest rate. Let K be the annual payment rate. So how much money are you paying every year? So that's in dollars per year. And we're going to let Y be the amount still owed at any time. So this is the function that's going to depend on time that we're going to try to solve for. And that, of course, will be measured in dollars. Okay. Now, here's the differential equation. So dy dt is the rate of change in the amount owed. Well, like as I stated at the start here, the amount owed changes for two reasons. One is the bank is charging interest. So every year they're going to charge you their interest rate times the amount that you still owe. Okay? And then you are going to owe less because you're going to pay K dollars. Now, in this setup, we're assuming two things. We're assuming that the bank is charging interest continuously. So even though it's, the interest rate is say 10%, they're not saying, oh, at the end of each year they're figuring out 10%. They're dividing the year up into infinitely many pieces and taking the interest rate into infinitely small pieces and doing it. Um, so it's charged, interest rate is charged continuously. Likewise, we're assuming that you pay continuously. Now, of course, that's not the way it works. You generally on a mortgage, you pay once a month or something like that. But this assumption of continuity and that just being sort of a little bit of money trickling out of your bank account all the time to pay that mortgage is essentially a simplifying assumption that allows us to use the differential equation and solve this problem more easily. The actual month by month solution takes a different way of looking at it, but the results are so close to the same that this is just an easier way to deal with it, to get an idea of what your monthly payments are going to be and how long it's going to take to pay off the loan, things like that. Okay. So the amount owed is changing for two reasons. Interest is being charged and you're making payments. So the amount owed goes up because of that, it goes down because of that, hence the minus sign. Okay. Now, this is both a first order linear and a separable differential equation, so I could solve it either way. And just because I've solved a bunch of them in the previous videos as separable, I'm opting for kicks here to do this as a first order linear. So I'm going to take the ry and move it over to the other side of the equation, so it's a minus ry over here. I've already got a 1 in front of the dy dt. So the integrating factor would be the e to the integral of p of t, but in this case, p of t is just minus r. So my integrating factor is e to the minus rt. Remember, with first order linear, what you're doing is you're taking that integrating factor, you're multiplying it on both sides of the equation, which makes the left-hand side precisely the derivative of y times the integrating factor. So when you integrate that, you integrate the derivative of y times the integrating factor, you get y times the integrating factor. On the other side, you have this thing times the integrating factor, and then integrate that. So this is what I need for the integral on that side of the equation. And yeah, so there's a u substitution with u equals minus rt, so du is minus r dt, so I end up having to divide by that negative r, which makes that a plus sign and puts an r in the denominator. Anyway, it's an integral of e to the u du, which is just e to the u, plus a constant. And then I'm going to solve for y by multiplying both sides by e to the positive rt, to get it to cancel out on this side. And I get this. Multiplying by distributing that in, I get this. And I think I said in the previous video too that when I was a student, I kept leaving the plus c on the outside, so when I multiplied here, I didn't get this times the c, and these would just cancel out, and I get a constant plus c. It's like, what? How does that work? How could this be a constant? But it isn't, because the e to the rt has to be multiplied by that. So this is the amount owed is some constant plus ce to the rt. And I have to admit that when I look at that, I think, really? This is an increasing exponential function. So it's like an amount I owe getting bigger and bigger and bigger. How is that working? But what's going to happen is c is going to be negative, hopefully. And then that'll be an upside down increasing exponential function, which will be pulling the amount owed down. Okay, so here we go. Let's plug that initial condition in. At time 0, the amount owed was the whole principal, p. And so the constant that you get is p minus k over r. And so the thing looks like this. Now, I can see a couple of things. If p minus k over r, sorry, if k over r is less than p, so p minus k over r is positive, then the debt is going to grow. If you're not paying enough, if they're charging you more interest than you're paying, then the amount you owe is going to go up. This is quite often the case that people have with their problem they have with their credit cards. But on the other hand, if k over r is greater than p, then the debt shrinks. That this becomes an upside down. This becomes negative, and so there's a horizontal asymptote at k over r, and then the function just drops off from there. An upside down increasing exponential function means that the debt will be decreasing, right? So if you wanted to know the length of the loan, right? So if you want to say, hey, I only have so much money to pay, you can say, well, we want to know t when y is equal to 0, right? When the debt is 0, how much time went by? So I plug 0 in for y and solve for t, and I end up with, let's see, so what happens here? Move this over to the other side, divide by that stuff, simplify that fraction. The way I simplify that fraction is I multiply top and bottom by r, so I'm multiplying by 1, but the top gets multiplied by r and the bottom gets multiplied by r, and the over r's cancel out. Actually, look at this denominator that I end up here. P times r is the amount owed times, so the original principal times the interest rate. So that's the interest that's going to be charged in that first year, and the minus k, that's the rate owed. If that is a if that's equal to 0, you got a problem. I mean, you're not ever going to pay it off. But this is the comparison here. PR minus K is definitely interest minus amount paid, and you want that to be negative because you want this more. There's a couple of things here. Yeah, you want that negative because there's a negative on the top that makes this fraction then a positive number, which could actually equal to e to the rt. On the other hand, if the k is not big enough, so PR minus k is negative, then this fraction is negative and there isn't any solution for t. You will never pay it off because you're not paying enough money each year. Right? from the point of view of a annuity, that might not be a bad thing. I mean, if you're taking out of your annuity less than what you're earning in interest, then that annuity will keep going, indefinitely. And that's how people set up, endowment funds or whatever, that they're going to have a bank account that always pays, so many dollars a year to some charity. They just set it up so that the amount taken out is less than the interest that's being earned. All right, and solve for Sir T, you end up with this thing right here. Right. Now this formula can be used in different ways. I solved for T because I wanted to say, if I know how much money I can pay annually, then I can figure out how much time it's going to take to pay off the loan. On the other hand, if you say I want it to be a 30-year mortgage, or from the point of view of an annuity, you say I think I'm going to live for another 30 years, and I want to run out of money right as I die. Right? It's like, then you might so you might want to go the other way. You might want to say, if I know the time limit, then you want to solve for K. What's the annual payments, right? So one way or the other, you're going to know one thing and you're going to solve for the other one. It's also a matter of, you can look at how the interest rate affects things here. That is, if you have so much you can pay for per year, then you want to say, well, how does the interest rate affect the length of the loan? Right? And it's actually fairly substantial. But lowering that interest rate is an important thing. And right now, in this crazy world that we live in, interest rates are really low. So if you're thinking of getting a mortgage, now's the time to do it. But anyway, so there is mortgages and annuities from the point of view of first order differential equations.